All right, this is the second video on the section 3.5, which is integration by tables. And so we're going to look at a couple examples of using integration by tables. So here we're looking at the integral of 2x divided by the square root of x to the fourth plus 25 dx. And looking through the formulas in the back of the textbook, we're going to try to use formula 72, which states that the integral of du over a squared plus u squared is equal to the natural log of the absolute value of u plus square root of a squared plus u squared plus c. So to see if this will fit, u would have to be x squared, du would be 2x dx, and u squared would be x squared squared, which would be x to the fourth, and a would need to be 5. So if we do that, 2x dx is du, x to the fourth is u squared, a squared would be 25, so this looks good. This looks like a good match. So this is going to be the natural log of the absolute value of u, and u was x squared, plus the square root of a squared, which would be 25, plus u squared, which would be x to the fourth, and then plus c. Okay, so natural log. The absolute values is not required because x squared and the square root of x to the fourth plus 25, that's all going to be positive. So we're going to be okay. We don't need the absolute value bars there. Okay, and so we got natural log of x squared plus the square root of x to the fourth plus 25 plus constant integration is our integral. So that one was pretty simple. We're going to look at another one that's a little more complicated. May require several integrals and maybe a couple integration formulas. All right, so we're going to look at the integral of e to the 3x plus 7e to the 2x plus 5e to the x divided by e to the 2x minus 100 dx. The first thing we're going to do is we're going to factor out an e to the x out of the numerator, and that may help with some sort of u substitution. Okay, so you factor an e to the x out of the top there, and then we're going to go ahead and do a u substitution. U is equal to e to the x, so du is equal to e to the x dx. So our integral becomes u squared plus 7u plus 5 all over u squared minus 100 du. Okay, and probably what we want to do is split this up into 3 parts. So the integral of u squared over u squared minus 100, and that u squared minus 100 is in a radical, plus the 7 times the integral of u over the square root of u squared minus 100, and plus 5 integral of du over u squared minus 100. Okay, and so we'll look at each one of those individually. I noticed that the middle integral, I'm probably going to be able to just use a regular u substitution, whereas the first and the third, those don't look like integrals that we normally integrate just with normal easy stuff like u substitution. So you probably have to do a trig substitution with the first and the third integrals, but we're going to look at our formulas. All right, so one of the formulas I looked up is formula 82, which says the integral of u squared over the square root of u squared minus 100 is going to be equal to u over 2 times the square root of u squared minus a squared plus a squared over 2 natural log absolute value of u plus the square root of u squared minus a squared, and then plus c. Okay, so that's going to be u over 2 square root of u squared minus 100 plus 100 over 2 ln absolute value of u plus the square root of u squared minus 100. So that's the first integral. Okay, now the second one, I'm going to do a substitution. Since we're already using the variable u, let's use variable a. So a is equal to u squared minus 100. So dA would be equal to 2u du. So we need to multiply by 2 and divide by 2 so we get an exact match. Okay, so that'd be 7 over 2, integral of a to the minus 1/2 dA. All right, now for the last integral there, we are going to look at formula 81. So the integral of du over the square root of u squared minus a squared is equal to the natural log of the absolute value of u plus the square root of u squared minus a squared plus c. So it's going to be 5 ln absolute value of u plus the square root of u squared minus 100 plus c. Okay. All right, so u was e to the x, so e to the x over 2, square root of e to the 2x minus 100, plus 50 ln absolute value of e to the x plus the square root of e to the 2x minus 100. I went ahead and got rid of the absolute value bars because it's not needed. E to the x and the radical are going to be positive. Plus, and we're going to go ahead and integrate 7 halves, a to the minus 1 half over here. So have 7 halves, a to the 1 half divided by 1 half plus c. So that's going to be 7 square root of a plus c. So 7 square root of u squared minus 100 plus c. So 7 e to the 2x minus 100 in the radical, plus 5 natural log of e to the x plus the square root of e to the 2x minus 100 plus c. I noticed that I have like terms, and so I had 50 here. I just erased it. So I had 50 there. So I got 50 of these and 5 of the same type, so we're going to combine that to make 55. Okay, so that's going to give us 55 of those, and then plus c. Okay, and so this one looked like we used 2 integration formulas and then a u substitution. There was probably maybe a formula for this also in the book, but in the back of the book we'd have to go look though. But if I can do a u substitution, let's just do a u substitution. It's simpler. Okay, we're going to look at one more integration by tables problem. So we're going to look at integrating x to the 5th times the square root of 3 plus 16x to the 4th dx. And after searching for a little while, this kind of looked like formula 69, which was the integral of u squared, square root of a squared plus u squared du. And you might be thinking, well, wait a minute, that doesn't really look like what we have. You got to be a little bit creative to get it to look like this. Okay, so this is going to be u over 8 a squared plus 2u squared, square root of a squared plus u squared, minus a to the 4th over 8, natural log of u plus the square root of a squared plus u squared, and then plus c. Okay, so we're going to have to be a little bit creative to get this to line up correctly. If we let u be 4x squared, then u squared would be 16x to the 4th, so that's looking good. Du would be 8x dx. Okay, so here's what we're going to do. We're going to slide out a 1/8. Okay, so we're going to multiply by 8 later on. So we got 1/8. Oops. And then times 1 over 16. And so where in the world does the 1 over 16 come from? The 1 over 8 is going to be coming from the substitution. We need an 8x dx. So here's what we're going to do. We're going to take that x to the 5th, and I'm going to write it as 16x to the 4th. So there I've multiplied by 16, and so I need to divide by 16 or multiply by 1/16 there. Square root of 3 squared plus 16x to the 4th. And then 8x dx. Okay, so you have x to the 4th and x, both of those out of the radical. That would make the x to the 5th. You got a multiplication of 8 and 16, and then we have a multiplication by 1/8 and 1 over 16, and so those all undo each other. Okay, so this is looking pretty good. So here we have a is equal to the square root of 3. All right, so 1 over 8 times 1 over 16, 1 over 128, integral of u squared. Square root of a squared plus u squared du. So that looks exactly like formula 69 now. So it'll be 1 over 28 times 4x squared over 8 times 3 plus 2 times 16x to the 4th, square root of 3 plus 16x to the 4th, minus 9 over 8, natural log 3 plus the square root of 9 plus 16x to the 4th, and plus c. Okay, I just caught a little bit of an error here. It should be u here, and u was 4x squared. And a was supposed to be, a squared was supposed to be 3. Sorry about that. So let's go ahead and fix that there. Okay. All right, so then we can factor out an 8. So we'll factor out an 8. So 1 over 1024. 4x squared times 3 plus 32x to the fourth. Square root of 3 plus 16x to the fourth. Minus 9. Natural log. So we have that error here also. So it's going to be a 4x squared. 4x squared plus, and not a 9, should be a 3. Okay. And plus 16x to the fourth. And then plus constant of integration. Okay. Alrighty, well that concludes this video on the trig. Oh, we're not doing trig substitution right now. What are we doing? We are doing integration by tables. Okay. So we'll see you next time.